Hi, this video is about wave interference, and there are two basic types of wave interference, constructive and destructive, and we'll take them in order. So constructive interference is when the crest of one wave meets the crest of another, or trough meets trough, and the amplitudes increase. If it was a sound wave, the amplitude would get larger and we would hear it get louder. So I've drawn that here graphically in three stages, 1, 2, and 3. So crest A is coming towards crest B, and when they meet, they add together and the amplitude gets larger. If it was a sound wave, we would hear it get louder. And then afterwards, B goes on its merry way and A goes on its merry way as well. In destructive interference, crest meets trough, or trough meets crest, and the amplitudes decrease. So here in point 1, stage 1, A is going to the right, crest A, and trough B is going to the left. And when they meet, they cancel one another. If they cancel completely, that's called completely destructive interference. If it were a sound wave, we would not hear anything. And then they reappear after their cancellation and go about their merry way afterwards. This is the principle behind noise-canceling headphones. I don't know if you've heard of those. Sometimes people buy them to wear on airplanes, on long trips. And they listen for a sound outside the headphone and then produce the upside-down version of it through the speaker and the headphone, and it cancels out some of the noise in the area. They have them in fancy cars too. So constructive and destructive interference. Now, if you're talking about sound waves and they interfere because when they're slightly different frequencies, you produce this phenomenon that we call beats. So beats form when sound waves of different frequencies interfere in an alternating pattern of constructive and destructive interference. Since they're slightly different frequencies, sometimes you have crest meeting crest, but at other times you have crest meeting trough. So sometimes the amplitude gets large and you hear it get louder, sometimes the amplitude gets smaller and you hear it get softer. So I've tried to draw that graphically here. I have a blue sine wave, I guess, and then a purple sine wave, which is a higher frequency, so more crests. And you can see that at some positions, the trough of the purple meets the crest of the blue, and that would give you a soft sound. They would tend to cancel, destructive interference. But at other positions, the troughs meet up and the crests line up and it gets louder. The amplitudes would add and increase. And then again, it cancels again, and then again, it meets again and it gets louder. I don't know about you, but when I talk about this with students, I typically think about, maybe you don't talk about it with your students, but what I'm about to say is probably something you've experienced. So if you've ever been sitting at a stoplight and you've got your turn signal on and the car in front of you has their turn signal on, and you kind of notice that for a few moments they're in sync with one another. They're blinking at the same time, and then a few moments later they're off sync. Yours is on and theirs is off, and then a few months later they're back in sync again. This is what happens with beats. Because those blinkers are flickering at slightly different frequencies, sometimes they match up and sometimes they're completely opposite, and then they match up again and then they're opposite again. Julius will demonstrate that for you on the video, and I can demonstrate it in class. Don't forget to ask me to do that. In any case, there's something called the beat frequency. That's the frequency at which it gets loud and soft. And so that's easy to calculate. And so write this down in your notes and on your cards. The beat frequency, the frequency at which it gets loud and soft, is just the absolute value of the difference in the two frequencies. So if you've got 256 and 258 hertz and you play them together, you're going to hear it get loud and soft 2 times per second. It has a beat frequency of 2 hertz. What's interesting, I think, is that when you have two people that are harmonizing, what you actually hear is each person's note. Say they're singing or they're playing an instrument. You hear each person's note individually, but you also hear the beat frequency note in between. And when that's correct, we call that harmony, and it's pleasing to the ear. Pretty fascinating stuff. Okay, last bit for this video is what's called a standing wave. So standing waves are formed because of wave interference, but they're a special kind of interference. So they form when a wave interferes constructively with itself or its own reflection. Now, how does that happen? How do you interfere with yourself, or how do you interfere with your own reflection? Well, I'll give you some examples here in a moment. But the important part to remember is that it's a constructive interference, And then only certain wavelengths and only certain frequencies will form standing waves for any given system. And so the first system I'd like to talk about is just a string that's fixed on both ends. That could be like a piano string or a guitar string or harp string, but it's fixed on both ends, it can't move. And so if you pluck that string gently, what you'll find is that the simplest standing wave pattern that can form on that string is when you get one big fat antinode. That's what this kind of clam shape there is. So the string goes up in the middle, it hits the end, and it reflects upside down back the other direction. And so that's called the fundamental note, or the first harmonic. And so that's the simplest pattern that can form. And if that pattern repeats, it reflects upside down, and then it reflects upside down, so this is upside down, so it flips right side up, and then back and forth, and back and forth, and back and forth. So it just reflects back and forth, and as it does so, it interferes constructively with itself. And when you plug it very gently, that's the note or the frequency that you would get. Now if you plug it a little harder, you can get it to vibrate in the second pattern, the second standing wave. And so you get an up and down, and it reflects back, like so. And if you plug it a little harder than that, you can get it to form the third pattern. So there's the incident wave and then the reflected wave. And again, it reflects back when it hits the other end. And they interfere constructively with themselves, or the reflections, I should say, and they form these standing wave patterns. We call them standing waves because it appears that the string appears, I said that twice, the string appears to stand still. So the pattern is constant. The string is moving, right? The string's moving up and down. But the pattern in which it moves up and down, and not when it's not moving, is constant. These fat parts are called antinodes, and the points in the middle here, where it's not much motion at all, that's called a node. In any case, each antinode, each clamshell-shaped figure, is half a wavelength. So here the length of the string is 1/2 lambda. Here we have two of them, that's a half and a half, which is a whole, or 2/2 lambda. And here we have half, half, and a half, which is 3/2 lambda. And so there's a pattern I hope you can see. It goes 1/2, 2/2, 3/2, 4/2, and so on. So if we take that pattern, we can derive an equation. So the length of the string corresponds to n divided by 2 times lambda, where n is a positive integer, 1, 2, 3, 4, 5, and so on. But we can also substitute in for wavelength. We know that wavelength is related to wave speed and frequency, given that equation from before. And so we combine this and that, and we get this green equation here. So this green equation are the frequencies that form standing waves on strings that are fixed at both ends. So the frequency is equal to what's called n, which is the harmonic number, times the wave speed on the string, however fast it's moving on the string, divided by twice the length of the string. And again, those n values can range from 1, 2, 3, and so on. They're always whole numbers, and they're positive integers. So when n is 1, that's called the fundamental. That's if you pluck the string, that's the frequency you're going to hear. Okay, that's the easiest way for it to vibrate, and that's typically its loudest note. If you pluck it, is that fundamental when n is 1. If you pluck it a little harder, you might excite an extra harmonic frequency, the second or the third or the fourth harmonic, and so on. Those have other names. Sometimes the second harmonic is called the first overtone, and the third harmonic is called the second overtone, and so on. So, sorry about the announcements. I don't know what to do. Most of our things will deal with the first harmonic. We're usually going to be concerned with the loudest note, the simplest mode of vibration. And so most of the problems you'll do will involve n equal 1. If it doesn't equal 1, you'll have to be told that. In other words, you're looking for the second harmonic or the third harmonic or so on. Let's do a simple example. Oops. Let's see if I can adjust this so it doesn't fall over on us. Let's say that we've got a guitar string, and it's 52 centimeters long, and it produces a frequency of 341.3 hertz, which is F, note F, when plucked gently. With what speed do waves travel on the string? We don't know. We haven't talked about how fast wave travels on strings, and that depends on a number of things. Julius told us it's the tension and the linear density and so on. So what we're given are our unknowns. That's over here. We're given the length of the string L, which is 52 centimeters. I converted that to meters, 0.52 meters. We're given the frequency, 341.3. And we're given the harmonic number. Now I don't come out in the problem and state that the harmonic number is 1, but it's plucked gently. So that's an indication that we're dealing with the simplest mode of vibration, which is n equals 1. And we're looking for v, the velocity. So the equation we'll use is the one we just had, F equals mv over 2L, where n is 1, 2, 3, so on. And we'll substitute our values into that equation. So 341 equals 1 times v over 2 times 0.520. And then we'll solve. So I'll multiply both sides by the denominator here, which is 2 times 0.520. And when I do that, I get v, and that's 355 meters per second. All right, thanks for watching.